Hello guys, welcome to Physics Grad. In this video we are going to discuss about conservation of momentum in terms of the Lagrangian formalism. And in our previous video we had learnt about conservation of energy. And we saw that energy is conserved when the Lagrangian was not explicitly dependent on time. That means dou L by dou t equal to 0. And this was a consequence of time being homogeneous, which means no 2 points in the time axis can be differentiated, or all of the points in the time axis are equivalent. So that is the property of homogeneous with respect to time. So in this particular case, that is the case of momentum, here we are going to consider the case, okay. So here we are going to consider the case when summation over a dou L by dou Ra vector is equal to 0. Here Ra is in the Cartesian coordinates. Okay, so what will happen when this particular condition is satisfied? So what does this mean? This means that the total partial derivative of the Lagrangian with respect to all the coordinates of the particles, the sum of them should be equal to 0. Okay, so before we fully understand the meaning of this, let us go ahead and do some math and see what is the consequence if this condition is satisfied, and later on with some examples we will try to understand what exactly this condition implies. Okay, but now we will just consider mathematically what is going to happen when this particular condition is satisfied, and then we will understand its physical significance through some examples, and thus making this condition more clear. Okay, so let's say that this condition is satisfied. Then from our Euler-Lagrange equation, for each a, okay, for every a, we will have d by dt dou L by dou Va vector is equal to dou L by dou Ra. This implies summation d by dt of dou L by dou Va is equal to summation dou L by dou Ra vector. But this condition says that this is equal to 0. This implies d by dt of the summation over a dou L by dou Va is equal to 0, which implies that the summation dou L by dou Va is a constant, and I am going to denote it by the capital letter P, and this particular constant, which is an integral of motion, okay, because it is just a function of the velocity and position, and not a function of time, because always this Lagrangian is of the form T of v1 v2 dot 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 minus u of r1 r2 dot 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 and time. So dou L by dou Va, so dou L by dou Va is just going to be dou T by dou Va, and this T is only a function of V. So this constant P, since it's expressed as a function of V's, that is a velocity, this is an integral of motion. as we have defined what an integral of motion is in our introduction lecture on conservation laws. And this I am going to call it as the total momentum. Okay, we are going to define or call this as the total momentum of the system. Okay, so when is this constant, or in other words conserved? So total momentum is, so therefore total momentum is conserved when summation over a dou L by dou Ra vector is equal to 0. Okay, so this is the condition for the total momentum to be conserved. So we are going to again denote this summation a dou L by dou Va. I am going to call this as summation over a Pa, where Pa vector is defined as dou L by dou Va. This is the momentum vector for ith particle. Then the total momentum vector P will just be equal to the summation of the individual momentums. Okay, so this is the nothing but the additivity property. We will come back to this more when we look at examples. Okay, but for now let's just leave it at that. Okay, all right. Now so far we were in Cartesian coordinates, where we were expressing each of the position in the r vector and velocities as v vectors. But what if there are constraints and we have to use generalized coordinates? Okay, so in terms of generalized coordinates, what do we have? So in terms of generalized coordinates, we define Pi as dou L by dou Qi dot, and we call this as the generalized momentum with respect to the so this is the ith generalized momentum. Okay, so this is the definition. Then when do we say that the total momentum, so the total generalized momentum will be equal to the sum of the individual generalized momentums. Alright, now when you take this sum, you have to be careful, because these generalized momentums will have so if they are defined along some particular direction, or if to make it worse, it may even have different dimensions also. So we cannot in the same sense as how we define the total momentum over here, that is here, the total momentum, we cannot write it as the sum of the individual momentum over here, because dimensions of Pi and Pj may be different, because our Qi and Qj may not have the same dimension, because we are choosing generalized coordinates. Okay, so we cannot define this total generalized momentum unless we know all the dimensions of what our generalized coordinates are. So for example, in the case of the pendulum, we saw that our generalized coordinates was the angle theta, whose dimension is not position, it's angular position. So even though in Cartesian coordinates we were representing the bob in terms of the Cartesian position vector, okay, which has the dimensions of length. So we cannot define total generalized momentum. However, our Euler-Lagrange equations give us d by dt of dou L by dou Qi dot is equal to dou L by dou Qi. Now, if dou L by dou Qi was equal to 0, this would imply d by dt of dou L by dou Qi dot will be equal to 0, or Pi is equal to constant, which implies conserved. Okay. So even though we could not say that the total momentum is conserved, because we cannot define total momentum as simply the sum of Pi's, because they may have different dimensions, we can, however, look at the individual generalized momentums and see whether it is conserved based on whether dou L by dou Qi is 0 or not. So if dou L by dou Qi is not equal to 0, then the corresponding generalized momentum Pi is not conserved. But if they are equal, if it is equal to 0, then Pi will be conserved. So we can do the same thing in the case of our previous exercise, wherein we used Cartesian coordinates, and say that if L was let's say if L was dependent on R1, R2 but not on R3, and let us just have 3 particles. Okay, this would imply that dou L by dou R1 is not equal to 0, dou L by dou R2 is not equal to 0, but dou L by dou R3 would be equal to 0. So if we have just this information, and also if dou L by dou R1 plus dou L by dou R2 is not equal to 0, then this is the only thing which is equal to 0, implies only P3 will be conserved. But P1, P2 and sum of P1, P2, P3 in any of the sum, whether all 3 are taken 2 at a time, is not conserved, because these quantities are not equal to 0. Okay. So let us consider an example. If you consider the projectile motion, then in this case, in the y direction, so if this is y and this is x, so we will have L equal to half m vy square plus half m vx square minus mg y. Okay, so this is of the form T minus U, where total kinetic energy is this part and total potential energy is this part. Then here we see that dou L by dou y is not equal to 0. It is in fact equal to minus mg, whereas dou L by dou x is equal to 0. So therefore only px is conserved. And that is what we see in a projectile motion, because the velocity in the x direction is constant and our momentum dou L by dou Vx becomes mvx, and since in our projectile motion the x component of velocity is constant, this is also constant, or in other words, because of this condition the x component of velocity is constant. Whereas in the vertical direction, that is in the y direction, this is not equal to 0, and therefore our d by dt of py will be equal to minus mg, which implies py is minus mgt plus some constant c determined by the initial condition. So we can clearly see that the value of py changes with respect to time, and therefore it is not conserved, and which is what we observe in our projectile motion. Alright, so I hope that much is clear. Let us continue. So now let us make some notes about some important points. Okay, so note: if L is not explicitly dependent on Qi, that is a generalized position, then dou L by dou Qi equal to 0, which implies dou L by dou Qi dot, which is Pi, is constant, which is what we had seen, or it is conserved. Also, the total momentum, again we saw that cannot, so this can't be defined in generalized coordinates unless the dimensions match. Okay, so if you consider, however, Cartesian coordinates, for example, okay, if you consider Cartesian coordinates, then we see that the total momentum is given by summation I dou L by dou V I vector, that is P. If so, this is nothing but the summation of the individual momentum, and therefore additivity is followed. And this is followed no matter whether there is interaction between the particles or not. So this is followed no matter whether there is interaction. But this was not the case in energy, where for additivity to be followed, the interaction must be negligible. Okay, so not the case in energy. So let us understand this with an example. So consider two masses m1 and m2 initially separated by infinite distance. Okay, so with some reference, I'm going to call this as R1. Okay, position of this by R1, position of this by R2, and initially R1 minus R2 modulus was infinity. Okay, then from the total energy initially is, so initially it is infinity and at rest. Okay, both are at rest. Then total energy is 0. Okay, which is kinetic energy plus potential energy. Kinetic energy is however 0 because it is at rest, but potential energy we define it as minus g m1 m2 by R modulus, where R is R1 minus R2. Okay, so when R is infinity, potential energy is also 0, so the total energy initially is 0. So initial energy. Okay, let us see what will happen as they approach each other. Okay, so as they approach, we will have m1 going with velocity v1 and m2 going with velocity v2. This again is position are represented by r1 and r2. Okay, then what is going to happen for the energy and what is going to happen for the momentum? Okay, so the Lagrangian for the individual particles is nothing but, so Lagrangian is of the form T plus U. So for particle 1 it is the kinetic energy half m1 v1 square. So if this is only in one dimension, that is this dimension, then we don't have to worry about other components, and I can drop the vector notation here. So this is equal to half m1 v1 square minus, so sorry, this L is T minus U, so minus U is nothing but this, minus G m1 m2 by mod R1 minus R2. Okay, similarly L2 is half m1 v1 square minus G m1 m2 by mod R1 minus R2. Okay, but L1 plus 2 is half m1 v1 square plus half m2 v2 square minus G m1 m2 by R1 minus R2. Okay, here we don't add these two again because the total potential energy is still minus G m1 m2 by R1 minus R2. So this is not equal to L1 plus L2. Why? Because there is interaction. So L equal to L1 plus L2 holds only when the interaction is negligible, but here there is gravitational interaction, and therefore the total energy E1 plus 2 is not equal to E1 plus E2. Okay, so additivity is not followed because there is interaction. However, dou L1 plus 2 by dou T is equal to 0, and the system defined by 1 plus 2 is closed. Okay, so closed, which implies E1 plus 2 is conserved, and E1 plus 2 as we defined, as we saw, is going to be T plus U, that is half m1 v1 square plus half m2 v2 square minus G m1 m2 by R. And what this tells us, and E1 plus 2 initial was 0, and since E1 plus 2 is conserved, at any point of time this must equal 0, which implies the increase in the potential energy or decrease in the potential energy is seen as an increase in the total kinetic energy, and that is what law of conservation of energy also says. However, if you consider the momentum, okay, then P1 is equal to dou L by dou V1. This is M1 V1, and P2 is dou L by dou V2, which is M2 V2. Individually, these are not conserved. Why? Because, so this is because dou L by dou R1 is not equal to dou L by dou R2 is not equal to 0. Okay, this can be seen from the definition of our potential. So dou L by dou R1, so let me write it here, dou L by dou R1 is nothing but dou U minus dou U by dou R1, which is G M1 M2 by mod R1 minus R2. Okay, so let us say that R1 minus R2 in 1D. So since this is 1D, we can say that just one component we can consider, that is R1 minus R2 is greater than 0. This implies dou L by dou R1 is equal to minus G M1 M2 by R1 minus R2 the whole square. Correct? But dou L, which is not equal to 0. So therefore P1 is not conserved, which is what we see, because as they approach to, closer and closer, their velocity increases and therefore their momentum also increases. Okay, so individually they are not conserved. However, P total, so 1 plus 2 is P1 plus P2, which is, so in one dimension we don't need vector notation, which is M1 V1 plus M2 V2. But if you see dou L by dou R2, this is equal to, for R1 minus R2 greater than 0, this is equal to plus G M1 M2 by R1 minus R2 the whole square, which is minus of dou L by dou R1. So what we see is that dou L by dou R1 plus dou L by dou R2 is equal to 0. So therefore the condition that summation dou L by dou RA over all A is satisfied, therefore P1 plus 2 is conserved. So the total momentum of the entire system is still conserved, but individually they are not conserved, and this is again seen by the fact that when these two move towards each other, the direction of momentum here is positive and here it is negative, so the total momentum will still be 0 if initially P1 plus 2 was 0, and this is 0 because initially we assumed them to be at rest. So the velocity increases in such a way that the momentum, total momentum, cancels each other. Okay, so what we have seen, additivity is still followed by the momentum no matter whether there is interaction or not. So in this case there was interaction, but still we could define P12 as P1 plus P2, but this was not the case for energy. Okay, so some final notes. We see that dou L by dou Ra, which we defined, becomes minus dou U by dou Ra, because L is equal to T minus U and only U is dependent on the position vectors. But this by definition is the force on ith particle. And if dou L by dou Ra equal to 0 implies Pa is conserved. This in turn implies from here Fa is 0. Okay, so therefore if the force on a particle is 0, the particle momentum is conserved. The particle's momentum is conserved. And what our Euler-Lagrange equations say is that d by dt of dou L by dou Q, VA is equal to dou L by dou Ra, which is another way of saying d by dt of Pa is equal to Fa, which is nothing but Newton's law, that is rate of change of momentum is equal to the force acting on the particle. And if this force acting on the particle is 0, rate of change of momentum is 0, and therefore momentum is conserved, which is what we see here also. Okay. But for total momentum to be conserved, we have summation dou L by dou Ri equal to summation Ifi equal to 0. That is, the total force on the system must be equal to 0. Even though the individual forces may not be 0, the total force must be 0, which implies for the case of two particles, F1 plus F2 must be 0. So these forces can only arise because of the mutual interaction between them, and this says that the force acting on the first particle should be equal and opposite to the force acting on the second particle, which is nothing but Newton's third law. Okay, so we get Newton's third law from our condition for momentum to be conserved for a system of two particles. Okay, again in terms of generalized coordinates, in generalized coordinates, we can similarly define Fi as dou L by dou Qi and call this as the generalized force. However, this need not have the dimension of the force in our conventional sense. This is in terms of generalized coordinates and this is generalized force, so this need not have the dimensions of or units of Newton. Okay, it can be anything depending on the choice of Qi's. Okay, it can be taught if we choose our Qi as angles. It will be force if we choose our Qi as some Cartesian position vector and so on. Okay, and one final thing to remember is that in Cartesian coordinates, the generalized momenta are the components of the vector Pa. Px x cap plus Py y cap plus Pz z cap. A. Okay, so this becomes the generalized momentum. So these are the generalized momentum which we talk about. However, in generalized coordinates, also in Cartesian coordinates, this has the form mvx, but this is not true in the case of our generalized momentum, and all we can say is that this is a generalized momentum is a linear homogeneous function of Qi dot. This is a linear homogeneous function of qi dot. That's all we can say. So to be more precise, let us consider some example. I need some space. Okay. So if you consider our t in our generalized coordinates, we already had seen that it is of the form g I k, some function of the generalized position vector, which is basically all the qi's, qi dot, qk dot. Okay, and the total momentum. Okay, again we cannot define it. The individual momentum, let's say individual generalized momenta, this is given by what? This is dou L by dou qi dot. Let me call this L. Because we have already used I. So this is nothing but dou T by dou QL dot, because U doesn't depend on QL dot, which is nothing but dou by dou QL dot summation IK GIK of Q QI dot QK dot. And we will see that when L becomes equal to I or K, when you differentiate this becomes a linear function in terms of Q dots, and that is what I mean by linear homogeneous function of Qi dot. So this will not in general be equal to m times v when you talk in terms of generalized coordinates. Only in Cartesian coordinates this will be mass times velocity. Okay, so I hope you have understood what has been taught in this video. See you next time.